In this video we're going to look at power switching, and in particular we're going to focus on the Thyristor and the TRIAC. So starting off with the Thyristor, used for DC power switching. So you need to be able to draw a Thyristor. If we draw one like that, it looks a little bit like a diode, but then you also have a leg coming off it, which is our gate, and then also labeling our anode and our cathode. It works in a similar way to a diode, that its current only flows in one direction, and once it is conducting, then once it remains conducting, then it will continue conducting unless you turn it off. To allow it to conduct, we need to have a forward bias voltage. So we need to have the anode more positive than the cathode. There needs to be sufficient current flowing anode to cathode, and we call this the holding current. And we also then need a minimum gate voltage / current. If we look at the circuit, this is a typical arrangement to turn the thyristor on, so that if we then press switch 1, then we get that gate current / voltage, which then enables the thyristor, and the lamp will turn on. And then as we've enabled the thyristor, then once we release the switch, then the thyristor will remain conducting and the lamp will turn on. We'll also look in a second at the other half of the circuit, which is to turn the lamp off. But if we look at a question, we want to find out this value of resistor here, then we need to do a little bit of a calculation. Okay, so for the thyristor to conduct, then the gate voltage, if we were given some characteristic information, in this case we need 1.2 volts here, and we need a current here of 100 milliamps. Okay, so therefore then looking at the value of this resistor, it's a case of just applying Ohm's law. So resistance is equal to voltage divided by current. So therefore we need 100 milliamps of current flowing through that resistor, and then the voltage across it therefore is going to be 15 minus the 1.2 volts, giving us a resistance of 138 ohms. Now if we were asked to do the E24 series value, then we would go for the next size down from the resistor that we've got, so that we maintain that minimum gate current. So why is a thyristor better than a transistor? Quite simply, it has a faster switching off to on, which ultimately makes it our efficient. We can look at this on a graph, and what we find with the graph of showing the characteristic is if we increase the voltage anode to cathode, we can keep increasing, but nothing will happen. And then as soon as we then apply the gate signal, and that could be at any point if we just keep increasing, as soon as we apply it, then it starts to conduct, and when it starts to conduct, then we get rapid conduction through it. So you normally end up with that backwards cycle, as then the voltage across the thyristor then drops once it starts to conduct. We then look at the circuit again, and moment with the thyristor off, then the voltage at P is going to be at 15 volts because it's not conducting, and the voltage also at Q is going to be at 15 volts. Okay, now we have to be very, very careful at what they're asking us, because at this point here it said what is the voltage at P, as though that we had got our voltmeter here like so, but very, very occasionally you might get asked what is the voltage across the lamp, and if it was the voltage across the lamp, as the lamp's not on, then the voltage would be 0 volts. Okay, so therefore we close switch 1, so then the thyristor turns on, so virtually no resistance there now, so then the voltage at P will drop to 0 volts, and the voltage at Q, we've not done anything Q, so it remains as it is. Then we decide that we want to turn the lamp off, so that we press switch 2. As soon as we press switch 2, then the voltage at Q goes to 0 volts, but as this side of the plate was at 15 volts and it's dropped by 15 volts, so effectively we've gone down, so we've taken away 15 volts, and this side of the plate must also go to minus 15 volts, and it's this then, the minus voltage there, because the anode is no longer greater potential than the cathode, so therefore the thyristor will then turn off like so. And in this table we've got a little bit of a trick line here. We're pressing both switches. If we press both switches, then yes, even though this will then go to stay at 0 volts, then we'll actually still turn the thyristor back on again, so will be at. So now just going back to this line here, so point P has gone to minus 15 volts over a period of time, then this point here will then gradually work its way back up as the capacitor slowly then discharges up to 0 volts. Okay, if we now move on to AC power switching, we're going to use a TRIAC, which is very much sort of two thyristors put together. So and its response looks very much like a double thyristor. So we have the same sort of idea that we can forward bias it, and it's not until we activate the gate voltage as then it can conducts. We get that signal current flowing through, and then the same happens when we apply the negative cycle. We can increase the potential across the TRIAC, but then as soon as we apply the gate voltage, then it then conducts like so. Okay, so here we have a typical circuit with TRIAC in. Now this circuit here has got a phase shift network in, allows us to adjust the power load, which comes down to the calculation. And the equation for allows us to look at the phase shift angle is equal to tan minus 1 of the value of resistance divided by the reactant capacitor. So if we then take, if we take a typical example, let's C equal 100 nanofarad, we can see that the frequency is 50 Hertz, and we'll make the value of our resistance equal to 23 kiloohms. Therefore, XC equals 1 over 2 pi FC. We've got 1 over 2 pi times by our 50 Hertz times by our 100 nanofarads gives us an answer of 31.83 kiloohms. So our phase angle, the phase shift that we've got, equals tan to the minus 1 of 23 kiloohms divided by 31.83 kiloohms. And putting that all together gives us a phase shift of approximately 36 degrees. So this formula that we've got here is on our formula sheet, and I would certainly recommend working it out in stages, because then you've got several points to where you can check your answer. But if you wanted to re-amalgamate the equation, then you could also say that tan theta equal to 2 pi FCR. Now, just before we move on, this circuit would work fine as it is, but one of the things that we can do to make this circuit better, rather than connecting it directly to the phase shift network, is we can actually put a TRIAC in between here and improve the switching that we get. So there we are. I've just placed the link with a TRIAC, so it looks exactly the same as a TRIAC, but this time it doesn't have the gate connection. Okay, so I've just made a note there. A TRIAC acts a bit like a double Zener diode, and when the breakdown voltage is reached, it allows us to turn on the TRIAC more quickly, ultimately reducing the power dissipation. So back to my point, improving the switching of the TRIAC. Okay, if we put it all together in a timing diagram, we said that our phase shift network was going to have a 36 degrees lag. Well, if we look at if we have our original signal, that's when our signal has gone through 90 degrees. So 36 degrees will be 1 square. So then our voltage across our capacitor is going to lag the main signal by 1 square. So we can just draw it in, and we just draw it so that it's reached a voltage just less than the actual voltage it's supposed to create, and then at this point here it will have gone back down to 0 volts, so we can bring it down there like so. So 1 square along, it will then reach its maximum, so we'll bring that up to there like so, liking it. So now Also shown on this part of the time diagram, we've got the firing voltage, the voltage that we require for the TRIAC to fire, to actually control the TRIAC. So at that point there, and then at that point there, green there, that point there. Okay. These are the points when it will cause our TRIAC to fire. So up until that point there, then the voltage will rise across our TRIAC, and then at this point here, which will bring it down to there, then at that point there in our phase, then the TRIAC will fire. So therefore the voltage across the TRIAC as it conducts goes down to 0 volts, and get to that point there, and then as we go into the negative cycle, then the voltage across the TRIAC then starts to increase. So we get the firing voltage then causes our TRIAC to conduct again, so then the voltage drops across it, and we end up drawing a waveform. So okay, so just to recap, that firing voltage causes the TRIAC to conduct, so the voltage across the TRIAC increases until we fire our TRIAC, and then the voltage across the TRIAC then drops to 0. So then the final part of the drawing, we've got the voltage across our load. Well, the voltage across our load, if this side is increasing at the same as this is increasing, but the TRIAC is not conducting, therefore the voltage across the load will be 0. And then as soon as our TRIAC then conducts, voltage across our load will have all of our supply across our load, so then we end up with signal rising like so. The signal drops down to 0, and then the voltage across our load will then go back down to 0 volts as our TRIAC is switched off. And as soon as our TRIAC fires, then we get all of the supply voltage across load again. And then that therefore then concludes this video on thyristors and TRIACs.